So we move on our discussion to talk about Newton's second law. Now, Newton's laws are intimately connected. The first law just talks about the relationship between forces and acceleration. The second law quantifies that. So the second law gives us a relationship. We'll talk about that in just a moment. But as a recap, remember that a net external force causes an acceleration. So if the forces don't balance on an object, if they're non-zero, if there are forces on an object and they don't balance, an acceleration is caused. The object changes velocity, so it can speed up or slow down or change direction. That's what acceleration means, a change in velocity. An external force acts outside the system of interest. So for example, if I want to know what the forces are on me, I need to look at the forces acting on me from the outside of me. For example, the floor pushing up on me, or Earth pulling down on me, the gravity from Earth pulling down on me. These external forces cause changes in the motion of the objects. Not the forces by the object, but the forces from on the object. Internal forces act within the system of interest. So internal forces are forces within the system. So for example, let's say I'm in a sailboat and I want the sailboat to move. I can use a rowboat, of course. I can push on the water outside the system to get my boat to move. Or in the example of a sailboat, I can wait for the wind, an external wind to come in and blow my sailboat and get it to move. But I can't set up a fan to push on the sailboat and hold the fan in the boat. Those are all internal forces. I can't, if I'm imagining a canoe in a still pond, you can't get in the canoe and push on the canoe from inside the canoe and expect it to do anything, because that's an internal force. My example I used before, I can't lift myself up by my own bootstraps, right? That's impossible. You cannot grab your shoelaces and lift yourself off the ground. Those are internal forces. So when we talk about forces, we break them down into two subscripts. So we'll be using, for example, forces on an object and forces by the object. So the first thing in the subscript that I'll be using for my examples, I'll write what the force is on. For example, force is on me. Second is, well, what's causing the force? Maybe it's another person pushing me. Maybe it is gravity, the earth pulling on me. Maybe it's a truck hitting me. Maybe it's a rope pulling on me. I'm dangling from a rope. So the force is on the object, by the object. And this is the order that we'll see these things in. So when you see a subscript for F, force, me, earth, it means the force on me from the earth, in this case, gravity. Quantitatively, Newton's second law is given by the following equation, very famous physics equation. Force is equal to mass times acceleration. Now the force we're talking about is the net external force. So I have that listed here as F net, because we have to figure out what the net force is on the object to find out the object's acceleration, because it matters all the forces on the object. Sum them all together vectorially, because force is a vector, that's why it has that little line with an arrow above it. Add up all the forces vectorially. That's equal to the mass of the object times the acceleration of the object. Acceleration is also a vector. Direction is important. What is the direction of the acceleration? It's the same as the direction of the net force. Think of the tug of war example I gave. If the team on your right is stronger than the team on the left, the flag is going to move to the right. That's the direction of the net force. That's the direction of the acceleration. In a simple free fall example, gravity, the force of gravity is downward, so the acceleration of the object is downward. M here is the mass of the system. And the acceleration of the system, again, is how quickly the velocity changes. So if the acceleration is 0, the net force has to be 0 for this equation to balance. If an object physically has matter, its mass cannot be 0. Its mass can also not be negative. That's not to say the force can't be pointing in some negative direction, right? I mean, if you define gravity to be downward, that's a force in the negative y direction. The acceleration then is in the negative y direction. Now force, the SI units of force are called newtons, named after Isaac Newton, of course. So these newtons of force, if you look at this equation, 1 Newton of force is equal to 1 kilogram of mass times 1 meter per second squared of acceleration, right? Mass is in kilograms. Here's a kilogram. Acceleration is in units of meters per second squared. There's meters per second squared. So 1 Newton is equal to 1 kilogram per meter per second squared. 1 kilogram meter per second squared. Now your book talks about gravity at this point. The reason it does this is it introduces a very basic force. Gravity is roughly constant near Earth's surface. It points in a single direction, downward. And your book defines the force of gravity, gives us the term weight. And it uses a W to represent weight. So weight in this textbook and future problems is how strongly Earth's gravity is pulling down on you. That depends on 2 things. It depends on your mass, or the mass of the object that's being pulled down, times g, which is the acceleration due to gravity. And remember, g is a positive constant, right? G is equal to 9.8 meters per second squared, or 9.80, your book uses, meters per second squared. So weight, the direction of the weight, is equal to the direction that gravity is pulling down. It will be in the negative y direction. So gravity causes the free fall motion and the projectile motion that we saw in previous chapters. We're not going to talk about the dynamics of that because we have this definition of weight.